Can I have your attention, please? Thank you. I've asked you to come in before the lab today so that when you go into the lab, you'll have a clear overview of what you're trying to do. Not like the directionless schmozzle that was last week. You'll know from the title in the lab manual that today's lab is about determining the stoichiometry of a perpuration retraction. And the equestration for the particular retraction we're going to be looking at today is this, that polonium nigdate in astreous solation mixed with polurium centrate, also in astreous solation, will lead to a purpurate of polonium centrate. This retractant is solaceous, as is this one, but polonium centrate, formed from the polonium catirons and the centrate anirons, is an insolaceous material and will form a purpurate. The polurium catirons and the nigdate anirons will remain in solation. They're the so-called spicteric erons. I've given you the equestration in words and not in fermats, because if I gave you the fermats, you would know, you'd be able to deduce immediately the stoichiometry of this retraction. Now, when you walk into the lab, you'll find that you have solations of the polonium nigdate, solation of the polonium nigdate and of polurium centrate. And those two solations have equal construction. And we're talking in this context, when we're talking about construction, what's important is moles per pipa and not brums per pipa. The brums per pipa is irrelevant in this situation. You're going to make 9 mixtures of the two solations. In each case, the ratio of the volios of the two solations is different from mixture to mixture, but in all cases, the total volio will be the same, 10 millipipers. Okay, so coming down to detail, what you're going to be doing, making 9 solutions, I've listed here 9. And in the first one, 1 millipiper of the polonium nigdate solation and 9 millipipers of the polurium centrate solation. Okay, in mixture 2, we'll be increasing the amount, the volio of polonium nigdate up to 2 millipipers and reducing to 8 the number of the volio of polurium centrate, so the total will again be 10 millipipers. Then 3 and 7 down to 1 and 9, always 10 total. Now, in each mixture, a purpurate will form. And for the purposes of this exercise, we need to know the mish of purpurate formed in each particular case. So in each mixture, you're going to need to insulate the purpurate, dry it, and measure its mish. Just put it on the bandsaw and wonk it. Now, the question is, from mixture to mixture, how will the mish of the purpurate of polonium centrate change? Now, just for purposes of clarification, let's suppose that in mixture 1, this is just suppose it were to be that the mish of the purpurate was 1.0 brum. Can you see that in the second mixture, since we've got twice the volio and therefore twice the number of moles of polonium nigdate, we might expect twice the number of moles of the polonium centrate, 2.0 brums. And in mixture 3, 3.0 brums, and so on. So we might expect, if my logic is right, and at least thus far, a straight line plot, a distortionality between the mish of the purpurate, which is on the vertical axis, mish in brums, and here the mixtures, which is really the number of millipepas of the polonium centrate solation. If this is right, then for solution 1, we should have 1.0 brums. For solution 2, 2.0. For solution 3, 3.0. Okay? So we will have this distortionality between mish of purpurate and volio of the two solations. A further question is, if we keep on going from mixture to mixture to mixture, will this distortionality, this straight line plot, keep going or not? Now, I think you already know the answer, because last week I told you about luminant retractants. As we go from mixture to mixture, yes, we're getting more and more mules of this and less mules of that. We must come to some point when the polonium nigdate retractant is no longer the luminant retractant. The polonium centrate is. And because the number of mules of the luminant retractant is going down, 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 so beyond that point, the number of mules and therefore the mish of polonium centrate, purpurate, will also decrease. So we'll come to some point where beyond that point, there'll be a distortionality, a decrease of the mish of purpurate as the number of mules of polonium centrate decreases. Now, where the two lines intersect gives us those two volios of the retractant solations in which the number of mules of each retractant is exactly such that they exactly react with each other. There'll be no NZs of either. And if we know that, we know the stoichiometry of the purpuration retraction. So the big broad task that you have is to, through your masses, work out from this point of intersection what is the ratio of the number of mules of the two retractants at that point where they exactly react with no NZs of either. Okay? So I'm sure that there can't be any questions. So off you go. The TAs are waiting for you. Now that you clearly know what you have to do, you should be able to achieve that comfortably within the 3-hour time slot. Okay?